Hey everyone, welcome to week 4 of building scalable distributed systems. And this week we're going to cover in 3 parts some issues concerning distributed systems foundations. In this first part we're going to cover a range of issues to do with communication systems, hardware and software, which are necessary components of any distributed system. Scaling a system naturally involves adding multiple independent moving parts. We run our software components on multiple machines and our databases across multiple storage nodes, all in the quest of adding more capacity. Consequently, our solutions are distributed across multiple machines in multiple locations, with each machine processing events concurrently and exchanging messages over a network. This fundamental nature of distributed systems has some profound implications on the way we design, build, and operate our solutions. This week's materials provide the basic nature of the beast information you need to know in order to appreciate the issues and complexities of distributed systems software. In this part, we briefly cover communication networks, hardware, and software. Every distributed system has software components that communicate over a network. For example, if a mobile banking app requests the user's current bank account balance, you can see here on the slide a simplified sequence of communications that will occur. First, the cell phone app sends a request over a cellular network addressed to the bank to retrieve the bank balance. The request is routed across the internet to where the bank's web servers are located. Third, the bank's web server authenticates the request, checking that it's really the user who it claims it to be, and sends a request to a database server for the user's bank balance. The database server reads the bank balance from disk and returns it to the web server. The web server then sends the balance back in a reply message addressed to the application. This message is routed over the internet and the cellular network until the bank balance magically appears on the screen of the mobile app. It sounds almost simple when you read the above, but in reality there's a huge amount of complexity hidden beneath this sequence of communications. Our bank balance example from the previous slide will inevitably traverse multiple different networking technologies and devices. The global internet is in fact a heterogeneous machine, comprising different types of network communication channels and devices that shuttle millions of messages a second across networks to their intended destinations. Different types of communication channels exist. The most obvious categorization is wired versus wireless, as shown on the slide. For each category, there are multiple network transmission hardware technologies that can ship bits from one machine to another. Each technology has different characteristics, and the ones we mostly care about are speed and range and reliability. For physically wired networks, the two most common types are local area networks and wide area networks, LANs and WANs. Local area networks are networks that can connect devices at building scale, being able to transmit data over a small number, say 1 to 2 kilometers. Contemporary LANs can transport 100 megabits per second to 1 gigabits per second. This is known as the network's bandwidth or capacity. The time taken to transmit a message across a local area network, the network's latency, is sub-millisecond with modern technologies. Wide area networks are the networks that traverse the globe and make up what we collectively call the internet. These long-distance connections are the high-speed data pipelines connecting cities and countries and continents with fiber optic cables. These cables support a networking technology known as wavelength division multiplexing, and this makes it possible to transmit up to 171 gigabits of data over 400 different channels, giving more than 70 terabits of data per second as the total bandwidth for a single fiber link. The fiber cables that span the world normally comprise 4 or more strands of fiber, and this gives a bandwidth capacity of hundreds of terabits per second for each cable. Latency is more complicated with wide area networks, however. Wide area networks transmit data over hundreds to thousands of kilometers, and the maximum speed that data can travel is the theoretical speed of light. In reality, fiber optic cables can't reach the speed of light, but do get pretty darn close, as you can see from the table here on the slide. So a message will take from New York to San Francisco around 20 milliseconds, whereas one from New York to Sydney crossing the Pacific and North America is going to be a minimum of about 80 milliseconds. One of the reasons that data doesn't transmit at the speed of light is that the data as it traverses the internet needs to pass through networking equipment called routers or routers. These are responsible for transmitting data on the physical network connections to ensure data is transmitted across the internet from the source to the destination. Routers are specialized high-speed devices that can handle several hundred gigabits of network traffic, pulling data off incoming connections and sending the data out to different outgoing network connections based on their destination. Routers at the core of the internet comprise racks of these individual routing engines, and hence can process tens to hundreds of terabits per second. This is how you and thousands of your friends get to watch a steady stream on Netflix every evening. Wireless technologies have different range and bandwidth characteristics. Wi-Fi routers that we're familiar with in our homes and offices are wireless Ethernet networks that use 802.11 protocols to send and receive data. The most widely used of these protocols, 802.1 AC, allows for a maximum theoretical data rate of up to 5,400 megabits per second. The most recent 802.11ax protocol, also known as Wi-Fi 6, is an evolution of previous technologies and promises increased throughput speeds of up to 9.6 gigabits per second. The range of Wi-Fi routers is of the order of tens of meters, and of course is affected by physical impediments like walls and floors. Cellular wireless technologies use radio waves to send data from our phones and devices to routers mounted on cell towers, which are generally then connected by wires to the core internet for message routing. Each cellular technology uses improved bandwidth and other dimensions of performance. The most common technology at the time of writing is 4G LTE wireless broadband. This is around 10 times faster than the older 3G standard and is able to handle sustained download speeds of around 10 megabits per second with peak nearer 50 megabits per second, and upload speeds between 2 and 5 megabits per second. Emerging 5G cellular networks promise 10 times bandwidth improvements over existing 4G, with 1 to 2 millisecond latencies between devices and cell towers. This is a great improvement over 4G latencies, which are in the 20 to 40 millisecond range. The trade-off is range. 5G base station range operates at about 500 meters maximum, whereas 4G provides reliable reception at distances of 10 to 15 kilometers. This whole collection of different hardware types for networking comes together in the global internet. The internet is a heterogeneous network with many different operators globally and every type of networking hardware imaginable. The figure on the slide shows a simplified view of the major components that comprise the internet. Tier 1 networks are the global high-speed internet backbone. There are around 20 Tier 1 internet service providers, ISPs, who manage and control global traffic. Tier 2 ISPs are typically regional, e.g. for each country, and have slower bandwidths than Tier 1 ISPs. They deliver content to customers through Tier 3 ISPs. These ISPs are the ones you pay for your home internet every month. There's a lot more complexity to how the internet works than described here. This complexity is beyond the scope of this course. From a distributed systems software perspective, we need to understand more about the magic that enables all this hardware to route messages from, say, my cell phone to the bank and back. This is where networking software and the IP protocol enter the scene. Software systems on the internet communicate using the Internet Protocol Suite. The Internet Protocol Suite specifies host addressing, data transmission formats, message routing, and delivery characteristics. There are 4 abstract layers which contain related protocols that support the functionality required at that layer. These are shown on the next slide. The 4 layers are depicted on here. Let's go through them from the lowest layer, the data link layer, to the highest layer, the application layer. The data link layer specifies communication methods for data that crosses a single network segment. This is implemented by the software that runs on the device drivers and network cards that live inside of our devices. It's very low-level, hardware-oriented. The Internet layer specifies addressing and routing protocols that make it possible for traffic to traverse the independently managed and controlled networks that comprise the Internet. So this is the IP protocol in the Internet Protocol Suite. The TCP layer builds on top of the IP layer and specifies protocols for reliable and best effort host-to-host communications. This is where 2 protocols, TCP and UDP, come in, and we'll talk about these a little more later. At the top we have the application layer, which leverages the underlying layers and comprises a number of application level protocols, 2 you will have heard of, being HTTP and SCP. So now let's look at the IP protocol in a little bit more detail. IP defines how hosts are assigned addresses on the Internet and how messages are transmitted between 2 hosts who know each other's addresses. Each device on the Internet has its own address. These are known as IP addresses. The location of an IP address can be found using an Internet-wide directory service known as the Domain Naming Service, the DNS. DNS is a widely distributed hierarchical database that acts as the address book of the Internet. The technology currently used to assign IP addresses, known as IP version 4, will eventually be replaced by its successor, IP version 6. IP version 4 is a 32-bit addressing scheme that before long will run out of addresses due to the number of devices connecting to the Internet. IP version 6 is a 128-bit scheme that will offer an almost infinite number of IP addresses. And to give you an idea of the usage of these two addressing schemes, in July 2020, about 33% of the traffic processed by Google.com was IP version 6. DNS servers are organized hierarchically. A small number of root DNS servers, which are highly replicated and reliable, are the starting point for resolving an IP address. When an internet browser or application tries to find a website, a network host known as the local DNS server that is managed by your local employer or ISP, in our case it would be Northeastern University, will contact a root server with the requested host name. The root server replies with a referral to a so-called authoritative DNS server that manages name resolution for, in the example shown on this slide, .com addresses. There's an authoritative name server for each top-level internet domain, such as .com, .org, .net, etc. Next, the local DNS server will query the .com DNS server, which will reply with the address of the DNS server, which knows about all the IP addresses managed by mybank.com on this particular example. This DNS is then queried and it returns the actual IP address where we need to communicate with. The overall scheme is illustrated here. As you can see, if you follow the numbers, this follows through the description we just went through. The whole DNS database is highly geographically replicated, so there's no single point of failure, and requests are spread across physical servers. Local DNS servers also remember the IP addresses of recently contacted hosts, so that the complete name resolution doesn't occur for every site we contact. This, of course, speeds up domain DNS lookup. So, when a browser or an application is armed with a destination IP address, it can start sending data across the network. IP has the task of delivering data from the source to the destination host based on the IP addresses in packet headers. IP defines a packet structure that contains the data to be delivered, along with header data including the source and destination IP addresses. Data sent by the application is then broken up into packets which are independently transmitted across the Internet. IP is known as a best effort delivery protocol. This means it does not attempt to compensate for the various error conditions that can occur during packet transmission. Possible transmission errors include data corruption, packet loss, and data duplication. We'll see why these occur shortly. In addition, as every packet is routed from source to destination independently, different packets may be delivered to the same destination via different network paths, resulting in out-of-order delivery to the receiver. Treating every packet independently is known as packet switching. This allows the Internet to dynamically respond to conditions such as network link failure or congestion on certain heavily congested routes, and is a defining characteristic of the Internet. As a consequence of this design, the IP protocol is unreliable, which can cause headaches for applications when data is lost. If two hosts require reliable data communication, they need an additional feature to make this occur. This is where the next layer, the transmission control protocol, enters the scene. So once an application or a browser has discovered the IP address of the server it wishes to communicate with, it can begin to exchange messages. In most applications, this is achieved using the TCP protocol, and in some applications, as we'll discuss later, the UDP protocol. These are the established standard transport protocols for the IP network stack. Distributed applications can choose which of these protocols to use. APIs for both TCP and UDP are widely available in mainstream programming languages such as Java and C++. In reality, use of these APIs is not common as high-level programming language abstractions hide the details from most applications. In fact, the IP protocol suite's application layer contains several of these applications, including HTTP, which is very widely used in mainstream distributed systems. And also on this slide, you'll see WebSockets, which is a HTTP alternative. Still, it's important to understand TCP, UDP, and their differences. The vast majority of traffic on the Internet is sent using TCP. TCP is connection-oriented, stream-oriented, and reliable. Let's explore what these three mean. First, TCP is a connection-oriented protocol. Before any messages are exchanged between applications, TCP uses a three-step handshake to establish a two-way connection between the client and the server. You can see this handshake at the top of the sequence diagram here by exchange of SYN and ACK packets. This connection stays open until the TCP client calls close to terminate the connection with the TCP server. The server responds by acknowledging the close request before the connection is dropped. This is actually a 4-packet exchange closing protocol. When a data stream is sent over TCP, it's broken up into individual network packets with a maximum size of 64K. Each packet contains a source address and a destination address, and these are used by the IP protocol to route the messages across the network. The Internet is a packet-switched network, as we said earlier, and this means every packet is individually routed across the network. The routes each packet can traverse can vary dynamically based on the conditions in the network, such as the failure of a network link or congestion at a particular router. This means the packets may not arrive at the server in the same order they are sent from the client. To solve this problem, TCP utilizes a sequence number, so the server can reassemble packets into a stream that is identical to the order that they were sent by the client. TCP is a reliable protocol, and reliability is needed as network packets can be lost or delayed during transmission between the client and the server. To achieve reliable packet delivery, TCP uses a cumulative acknowledgement mechanism. This means a receiver will periodically send an acknowledgement package that contains the highest sequence number of the received packets. This implicitly acknowledges all the packets sent with a lower sequence number. If a sender doesn't receive an acknowledgement within a timeout period, then a packet can be resent as it is assumed to be lost. TCP has many other features such as checksums to check packet integrity and dynamic flow control to ensure a client doesn't overwhelm a slow server by sending data too quickly. Along with connection establishment and acknowledgements, this makes TCP a relatively heavyweight protocol which is trading off reliability over efficiency. This is where UDP comes into the picture. To overcome some of the inefficiencies that are inherent in TCP, UDP is a simple connectionless protocol which exposes the user's programs for any unreliability of the underlying network. Using UDP, there's no guarantee of in-order delivery of packets, or even delivery for that matter. If a packet is lost, UDP will do nothing to recover. It can be thought of as a thin veneer or a layer on top of the underlying IP protocol, and deliberately trades off raw performance over reliability. This, however, is highly appropriate for many modern applications where the odd lost packet has very little effect. Think of streaming movies on Netflix, or streaming audio, video conferencing using Zoom, or gaming, where one lost packet has very little effect on the user experience. This slide summarizes the differences between the two protocols. On the left here you see UDP, where the sender and the receiver just exchange request and response messages. There's no attempt to set up a connection or tear one down. On the right you see TCP, where there's the connection establishment phase using the SYN message and an acknowledgement message which sets up the sequence number for acknowledgements. And then requests are sent and responses piggyback the acknowledgement of the highest seen sequence number. And this acknowledgements are sent between clients and servers to make sure that the stream of messages is reliably received. Not shown on here is the teardown phase that's also inherent in the TCP protocol. So that's a quick overview of communications hardware and the major protocols that are used in our software systems. Next, we're going to step up a layer and look at something called remote invocation or remote procedure calls, which build on this communications infrastructure to provide higher level programming abstractions.